Hello everyone. Today we'll be doing one of the modules of Edexcel Mathematics M1 or Mechanics 1, Chapter 2 Constant Acceleration. Now although this is Edexcel, but similar concepts apply to the M1 of Cambridge. So let's get straight to it. Distance is the actual length traveled. It is a scalar quantity. Displacement is the straight line distance from initial to the final point. It is a vector quantity. Don't worry if you don't understand these definitions at this point. We'll look at an example. Suppose you start from this point right here. This is your initial point, I for initial. You travel 10 meters in this direction and then 3 meters in the other direction. So the total distance that you have traveled is the actual length that you have traveled, that is 10 plus 3, 13 meters. Displacement on the other hand is the straight line length from initial to the final point. It is a vector quantity. Okay, so displacement is what? The straight line length from the initial to the final point, that is 7 meters. That's for 7 meters. Now notice that displacement is a vector quantity. So when you say displacement is 7 meters, you also have to say in which direction you have displaced yourself. There are 3 ways to specify your direction. You can simply say that I have displaced myself to the right. Now why particularly to the right? Because the definition says that displacement is the straight line distance from initial to final, from initial to final. So in this direction. So to the right. So to the right. Or if the question specifies the directions in terms of north, south, east, west, then you can say that I have displaced myself 7 meters east of the initial or east of the initial point. Or you can specify a sign convention before starting the sum and say that I will take the rightward direction as positive and say that I have displaced myself positive 7 meters. This positive means right. And how does the examiner know that this positive means right? Here you have specified before starting the sum that positive means right direction. Now we will look at an example where we will have a negative displacement. Let's see how that happens. Imagine that you start from your old initial point, travel 10 meters, but this time instead of traveling only 3 meters, you travel all the way behind your initial point, a total of 15 meters. Okay, so that's your final point. So that's your initial point and here is your final point. So what is the distance that you have traveled? Simple. The total length, the arithmetic sum of your length, that is 10 plus 15, 25 meters. That's the distance that you have traveled. The displacement on the other hand is the distance from the initial to the final point, that is this much, 15 minus 10, 5 meters. 5 meters. That's your displacement. Okay. Now when you say 5 meters displacement, you also have to specify the directions. So we can say that 5 meters to the left, or we can say 5 meters west of initial, or you can say negative 5 meters. Okay, but if you say that you have traveled negative 5 meters, you have to specify what this negative means. You have to specify before starting the sum that right will mean positive. Right will mean positive. So negative will mean that you have traveled in the left direction. You have displaced yourself in the leftward direction. Okay, and if you say that you have traveled west, then you have to draw a compass. This means north. Now we will see why the definition of displacement specifies straight line length. See, if you travel in this circular path a total distance of 20 meters, then the distance is 20 meters. I think you have already guessed it. The distance is 20 meters. The displacement on the other hand, if that's your initial point, that's your final point, your displacement is this straight line distance over here, the straight line distance. That is, let it be 8 meters. Okay, 8 meters to the right. That's your displacement, the straight line distance. Now we will see displacement time graphs or ST graphs. S for displacement, T for time. The gradient of a displacement time graph gives us velocity. Gradient means steepness. In this graph, the steepness or the gradient is 0. It is horizontal straight line, so it doesn't have a steepness, 0. So since the gradient is 0, the velocity also is 0. In this diagram, there is a constant steepness. There is a constant positive steepness, right? There is a constant positive steepness. So the velocity has a positive constant value. that could be positive 2 meter per second, that could be positive 10 meter per second, but it does have a positive value and the value is constant. It does not change from 2 or it does not change from 10. In this diagram, the gradient or the steepness is increasing, it is getting steeper, so the gradient is increasing, so the velocity is also increasing. In this diagram, the steepness is decreasing, so the gradient is decreasing, and gradient of displacement time graph means velocity, so the velocity is also decreasing. This is a basic idea of how to interpret a displacement time graph. Now we will be looking at a math. This is a displacement time graph. The displacement has been given in meters and the time has been given in seconds. For this sum, we will find the average velocity for each segment. What are the segments? We have 3 segments in this sum. 1, 2, 3. In the first segment, there is a constant gradient, so there is a constant velocity. Here the gradient is 0, so there is a 0 velocity, or the particle is stationary. Here the gradient is negative, constant negative, so there is a constant negative velocity in this segment. We will find the velocity for each segment. Okay. Before that, we have to learn 3 formulae. The first formulae is displacement is equal to the final position minus the initial position. The second formulae is velocity is equal to displacement by time, and the speed is equal to distance by time. So velocity is equal to displacement by time and speed is equal to distance by time. Don't get confused. We have already learned the difference between distance and displacement. So the average velocity for each segment. Let us start with segment number 1. In segment 1, we need the average velocity, and the formula of average velocity is displacement by time. What is the displacement? The displacement for segment 1 is the final minus initial position. So this is your final position, that's your initial position. So 10 minus 0, that is 10 meters. That's your displacement. What is the time? The time is 2 seconds. So what is the velocity? The velocity is displacement by time, that is 10 by 2, that is a positive 5 meters per second. So we are done with the first segment. For the second segment, once again, the average velocity is the displacement by time. Okay, so what's the displacement? Displacement is the final minus initial position. The final position is 10, the initial position is also 10. The time taken is 4 minus 2, that is 2 seconds. That is 0 by 2 is 0 meters per second. See, we have already discussed that when the displacement time graph has a horizontal line or 0 gradient, the particle is stationary, or whatever that's traveling is stationary. So here it has already been proven by the formula. Third segment, the velocity is once again displacement by time. Displacement is final minus initial position. The final position is 0. That's the final position. That's our initial position over here. That's 10. And the time is 5 minus 4. That is 1 second. So the velocity is minus 10 meters per second. Moving on to the next part of the sum. Finding the average velocity for the entire journey. Since we're talking about the entire journey, that is our final point and this is our initial point. Displacement is final point minus initial point. So the final point has a 0 displacement, so 0. Initial point also has a 0 displacement, so 0. So 0 minus 0 by 5, that is 0 meters per second, is our average velocity for the entire journey. Okay. So keep in mind that even if you travel a lot of distance, if you come back to your initial position, your initial point, then the displacement will be 0, and so the velocity, the average velocity, will also be 0. Moving on to the last part of our sum, the average speed for the entire journey. Not velocity, but speed. The formula for average speed is distance by time. So let us calculate the distance for each segment of our journey. In the first segment, we have traveled 10 meters, 0 to 10, 10 meters. Here goes 10. With the second segment of our journey, we did not travel any distance. See, for the entire 2 seconds, from 2 to 4 seconds, the particle or whatever that's traveling remained 10 meters away from its initial point. It did not change its position. So the distance traveled was 0. For the final segment, we have also traveled 10 meters. So here goes 10 meters. 10 plus 10, 20 by 5, 4 meters per second. This 5 is the total time, 0 to 5 seconds, 5, 4 meters per second. And with that, we are done with the final part of our sum. Now we will see what negative displacement looks like on the displacement time graph. Imagine that you start from this point to travel 10 meters. So this is what your displacement time graph will look like. Yes, and t, travel 10 meters. Then you come back to your initial point 10 meters, come back to your initial point 10 meters. Okay. Then you travel a further distance of 3 meters in the negative direction. Okay. So here we go, minus 3. This is what a negative displacement looks like in the displacement time graph. Now we will look at velocity time graphs. Don't get intimidated by looking at so many graphs. I have first drawn the displacement time graphs, and from the displacement time graphs I will try to deduce the velocity time graphs using the concept that the gradient of the displacement time graph gives us velocity. Okay, so let's begin. In this first graph, the displacement time graph has 0 gradient, it is horizontal, so the velocity is also 0. Let me draw the pen, 0 velocity. Here the displacement time graph has a positive gradient, right? A positive gradient, positive constant gradient. So the velocity is constant and it has a positive value. This value is definitely positive since it's above 0. Here the gradient of the steepness of the displacement time graph is increasing, so the velocity is also increasing. Now, not necessarily the velocity will be increasing at a constant rate in a straight line. The velocity could also be increasing in a curve like the displacement time graph. It is not possible simply by looking at the graph whether the velocity is increasing at a constant rate or at an increasing rate. Similarly, in this diagram, the steepness or the gradient of the displacement time graph is decreasing. So the velocity should also be decreasing, but we don't know whether the velocity will be decreasing in a straight line or in a curve like this or like this. But for sure we know that the velocity is decreasing because the steepness of the displacement time graph is decreasing. So these are the main types of velocity time graphs that we may come across. Now we will try to learn some more details about the velocity time graph. The gradient of the velocity time graph gives us acceleration, the area of the velocity time graph gives us displacement. In this math we have 3 segments, segment 1, 2, 3. In the first segment there is an acceleration because the velocity is increasing. In the second segment there is a constant velocity, and in the third segment there is a deceleration, the velocity is decreasing. The first part asks for the acceleration in segment number 1. Okay, so doing part A, acceleration in segment 1. Acceleration according to this formula is final velocity minus initial velocity. What is the final velocity? This is my final velocity, that is 10. My initial velocity is 0 and the time is 2 seconds. So 5 meters per second squared. That is the unit of acceleration, meters per second squared. You might as well want to put a positive sign indicating that the particle is indeed accelerating, not decelerating. And we will see why that happens in part B. They ask for the deceleration in the third segment. But let us continue with the formula of acceleration. Final minus initial velocity. In the third segment, the final velocity is 0, the initial velocity is 10, and the time taken is 1 second, 1. So that gives us a negative 10 meters per second squared. A negative acceleration. A negative acceleration means a deceleration. But since the question asked for a deceleration, so we will give our answer in terms of deceleration. The deceleration is 10 meters per second square. When you say deceleration, you don't have to put the minus because deceleration already means that the velocity is decreasing. It has a negative vibe to it. So you don't have to put the minus sign when you say deceleration. Done with part A and B. Part C asks for the total displacement. We know that the total displacement of the velocity time graph will come from the area. So let us try to find the area of this velocity time graph. If you want, you can find the areas individually. Segment 1, 2 and 3. This triangle, this rectangle and this triangle again. But here I am finding the total area using the trapezium formula. Trapezium formula for the area, displacement is area. Trapezium formula is half into height, that is 10, into sum of parallel sides. So that's one of the parallel sides, 5, and this is the other parallel side, that is 2. So 2, 5 plus 2, 7, 35 meters. That's our total displacement. Now we will look at another math of the velocity time graph. In this question, it is said that the total displacement of this velocity time graph is 600 meters and they want us to find the value of t. Let us use the same formula. For the velocity time graph, we know that displacement can be found from the area. The question says that the displacement is 600 meters, so we just put 600 meters in the place of displacement. Area. The area of this entire velocity time graph can be found using the formula of trapezium, that is half into height 8 into sum of parallel sides. This is one parallel side, this is one parallel side. So this parallel side has a length t plus 5t plus 40, t plus 5t plus 40. The other parallel side is this, and this has a length of only 5t, 5, sum of parallel side, the addition of the parallel sides. After simplifying, the value of t comes to be 10. And from here onwards, the question can ask a range of other parameters, for example, the acceleration in the first part, the deceleration in the second part, or the displacement in only the first segment or the first part, or the displacement in the constant velocity region. So be sure that you are confident how to find these parameters. Now we will learn to sketch the velocity time graphs of two bodies under the same axis. Take this motorcyclist M and the car C, for instance. The motorcyclist M starts from rest, has a constant acceleration for 8 seconds and then maintains a constant velocity. Car C also starts from rest, has a constant acceleration for 4 seconds, then maintains a constant velocity. Not necessarily that car C and the motorcyclist M have the same acceleration. So the gradient of these accelerating parts might not be the same. Now let us understand what overtaking means. Overtaking, take these two particles, for instance. Let A travel a distance of 10 meters in a time of 5 seconds. If B wants to overtake A, then B also has to travel a distance of 10 meters in the same 5 seconds, or else B can't overtake A. Which means, overtaking means both these particles being at the same position at the same time, or both the particles having the same displacement at the same time. So overtaking means both these particles having the same displacement. Keep this in mind. Now let us try to construct the velocity time graph of both these particles. M accelerates for 8 seconds, then maintains a constant velocity. C starts from rest, accelerates for 4 seconds, then maintains a constant velocity. That's 4, that's 8. Okay. If this is the case, this is C and that's M. From this graph we can see that the area under the curve of C, under the graph of C, will always be less than M. So C can actually never overtake M, because overtaking means having the same displacement, and the displacement of the velocity time graph is found from the area. So since the area of the C will always be less than M, so C can never have the same displacement as M, and so C can never overtake M. So this velocity time graph is wrong. M accelerates for 8 seconds. Now, C accelerates for 4 seconds, then maintains a constant velocity. Now there is a chance for the graph of C to have the same area as the graph of M. Okay? So this is the correct velocity time graph of both these bodies combined. Take a moment to understand this part intuitively. This may seem a bit difficult at first. Moving on to acceleration time graphs. Here I have 3 acceleration time graphs and 3 velocity time graphs. In the first acceleration time graph, the acceleration time graph is coincident with the x-axis or the t-axis. It has a constant 0 value, which means there is no acceleration, there is 0 acceleration. 0 acceleration means there is no change in velocity, so the velocity time graph will have a constant value, like this, a horizontal line. Okay. In this acceleration time graph, there is a constant acceleration you can see that there is some acceleration, maybe 2 meters per second square, but the acceleration is not changing with time. There is a constant acceleration. So the velocity time graph will look like that. Why? Because we know that the gradient of the velocity time graph gives us acceleration. So the acceleration is constant. So the gradient of the velocity time graph must also be constant, or the steepness of the velocity time graph must also be constant. Here it is important to notice that this acceleration has a positive value, so the steepness or the gradient also has a positive value. It is upward rising. On the other hand, in this diagram there is a constant negative value, for example -2. Okay, so the velocity will also have a will also be a straight line, but the gradient will be negative, a straight line with a negative gradient, because the acceleration is negative, and the velocity time graph's gradient gives us acceleration. So summing up, since the acceleration time graph is having a constant value, so the steepness will be constant, and since this acceleration is negative, so the gradient will also be negative. Now we will see how to find the final velocity using information about the initial velocity and the acceleration time graph. Okay, so the question tells us that the initial velocity was 10 meters per second and some acceleration has taken place in these 4 seconds. In the first 2 seconds, the acceleration was 2 meters per second square. From 2 seconds to 4 seconds, in the last 2 seconds, the acceleration was -1 meter per second square, or the deceleration was 1 meter per second square. We know that the area of the acceleration time graph gives us the change in velocity. So let us find the area of this acceleration time graph. In the first segment, the area is 2 into 2, that is 4. In the second segment, it is 2 into 1, that is 2. Since this part is above the time axis, so this adds to our velocity. On the other hand, this part is below the time axis, so this decreases our velocity. Another way of thinking is that 2 has a positive value, so this is acceleration. The velocity increases, so +4. And here the acceleration has negative value, so this is a deceleration. So in this part the velocity decreases, and hence the minus. So our final velocity will be 10 plus 4. 10 is the initial velocity, plus 4 from the first 2 seconds, and then in the last 2 seconds the velocity decreases by 2 meters per second. So the final velocity is 12 meters per second. Now let us see how to plot or how to sketch the velocity time graph from the acceleration time graph. The question tells us that our initial velocity was 10 meters per second, so we begin here. In the first 2 seconds, the velocity goes from 10 meters per second to 14 meters per second. So this is where our velocity goes, and the acceleration is constant, so the gradient of the velocity time graph is also constant. That is, the velocity time graph is a straight line. In the next 2 seconds, the velocity goes to 12 meters per second. We know that when the time is 4 meters per second, our velocity will be 12. So this will be our final velocity, 12 meters per second. So the velocity time graph goes from here to here. This is our final velocity time